In this video, we're going to look at MATLAB and how it handles systems of linear equations. Just a reminder that when we're working in MATLAB, most of the variables that we're dealing with, if they're numeric in nature, are going to be treated as matrices, even if in other languages they might be defined more simply. For example, if we have a single number, that would be a 1-by-1 matrix. If we say x equals 5, that's the same thing as making a single 1-by-1 matrix, single cell matrix 1-by-1 that has the element 5. Also vectors, as a row vector, it could be considered just a vector by itself, but in MATLAB it's going to be considered a 1 row by n column matrix. And likewise, if we have a column vector, it'll be n rows and 1 column. So everything fits into this paradigm of a matrix, even if it is a scalar or a vector in sort of the more natural definition. Now, why is this important? Why would someone develop an entire system based around matrices as the building blocks? Well, of course, you've seen in a linear algebra class that if you're solving linear systems of equations or systems of linear equations, then writing those systems out in a matrix form makes it easier to work with. Another example would be working with eigenvalues and eigenvectors. And those have really deep connections to differential equations and their solutions. There's also a pile of other connections. If you go into quantum theory and things like that, there's eigenfunctions that come out of that system, and it's all related back to linear algebra and matrices as well. And maybe a little more esoteric, but the system that Google started with in terms of ranking pages, it's hard to go back now and think about this now that they've been a monopoly player in the search space for a while. But they had a system called PageRank that really distinguished them from the competition at the time when they developed it. And it was a way that was based on eigenvalues and eigenvectors and a matrix representation of how different websites were connected to each other. And that allowed them to rank more highly interesting sites for search engine purposes. So there's a whole pile of examples of where matrices come in. Fast Fourier transforms use matrices. Anyway, there's a whole pile of applications that make MATLAB an interesting tool because of that fundamental matrix structure. For our purposes for now, we're going to be looking at linear equations, like the example down here below. Now, these kinds of problems can be solved systematically using Gaussian elimination, which is essentially row operations on this collection of equations. However, in your linear algebra class, you would have seen that if we write this system of equations in a matrix form, it becomes just easier to work with the row operations, because the row operations really only work on the coefficients of the variables and don't change the variables themselves. If we take this as an example, we can convert this system of equations written out long form into a matrix form. And the process here is quite simple. It just relies on the matrix multiplication idea. If we have the three variables a, b, and c, and we write them as a column vector, and then we match that with the coefficients only, so here 1, 2, and 3, as a row in a matrix, that becomes our a, that becomes our x, and the matrix multiplication properties will multiply 1 times a, 2 times b, plus 3 times c, and give us exactly what's on this left-hand side. We can then match that with the number 9, which is that matching element on the right-hand side. What we've done here is not transform the equations, but simply write them in an alternate format that's identical to what we have listed out long form here if we expand it. It's like factoring and unfactoring a polynomial. We can repeat that same procedure, taking the coefficients for the a, b, and c in order, listing them in the matrix here, recognizing that we would have 2 times a minus b plus 1c, which captures exactly what's on this row, and that would equal a single value in the second row here, which we'd say was 8. And last but not least, we have a 3. There's 3a, there's no b's, so we put a 0 in here, and then a minus 1 for the c value. And that altogether gives us a times x equals b, where this x vector is unknown, and what we're trying to solve for. The coefficients of those a, b, and c values end up in the matrix A. The constants on the right-hand side that are not related directly to a, b, and c end up on the right-hand side as a column vector here, 9, 8, 3. And again, this is exactly the same as this system here. We just happen to parse out the three variables and separate them from the coefficients. It means we can actually operate on these coefficients by themselves to hunt down what the values are for a, b, and c. What we're going to do, though, is not do that ourselves, but let MATLAB do that heavy lifting for us.